Hey there, and welcome. Today, we're diving into something you do every single day, looking in a mirror. But we're going way beyond the flat mirror on your wall to really understand the physics of curved mirrors, and more importantly, how you can absolutely ace this topic in your exams.
So, have you ever caught your reflection in the back of a shiny spoon and wondered, why do I look so weird? Sometimes your face is stretched out, sometimes it's squash, and sometimes it's even upside down. Well, today we're going to solve that exact mystery. So, to get to the bottom of this, we first need to meet the two main characters in our story, concave and convex mirrors. Honestly, understanding the difference between these two is the most important first step.
And the difference is actually super simple. Just grab a spoon. A concave mirror caves in, right? It's curved inward, just like the part of the spoon that holds your soup. Its job is to bring light rays together or converge them. A convex mirror is the total opposite. It bulges out, like the back of the spoon, and it spreads light rays apart, or diverges them. Just remember this: concave converges, convex diverges. Simple. Now, before we get any deeper into these curved mirrors, there's one golden rule of light that works for every single mirror out there, whether it's perfectly flat or totally curved. And here it is, the law of reflection. It sounds fancy, but it's so easy. It just says that the angle light hits a mirror is always equal to the angle it bounces off. That's it. The incoming angle equals the outgoing angle. Remember that because it's the foundation for literally everything else we're going to talk about. So you might be thinking, if that law is always the same, what makes curved mirrors act so differently? Well, it all comes down to a special line we call the normal. Just imagine a tiny flagpole sticking straight out at a 90-degree angle from any single point on the mirror's surface. With a curved mirror, the direction of that flagpole, the normal, changes everywhere you go. And that is the secret. Okay, now for the part that's going to help you crush your exams. We're going to learn how to draw with light. Think of these as 3 simple rules, kind of like cheat codes, that let you figure out exactly where an image will show up, no complicated math needed. But first, a super quick vocabulary check. The pole, P, is just the dead center of the mirror. The center of curvature, C, is the center of the big imaginary ball that the mirror was sliced from. The focus, F, is a really important spot where parallel rays of light meet up. And the principal axis? That's just the main straight line that goes through all of these points. Got it? Awesome. All right, rule number 1. This is the big one. Any ray of light that comes in parallel to that main principal axis will always bounce off the mirror and pass right through the focus point, F. That's it. Parallel in, through the focus out. Now for rule number 2, which, you'll love this, is just the exact reverse of rule number 1. If a light ray goes through the focus first and then hits the mirror, it'll bounce off and travel perfectly parallel to the principal axis. See? It's a perfect two-way street. Through the focus in, parallel out. And finally, the easiest one to remember, rule number 3. Any ray of light that goes through the center of curvature, C, and hits the mirror, just makes a perfect U-turn. It reflects straight back along the exact same path it came from. This one is a lifesaver when you're drawing diagrams. Okay, we've got our 3 rules. Now it's time to put them to work. Let's start making some images and finally figure out why your reflection keeps changing. This table basically shows you the superpower of a concave mirror. It's all about where you put the object. Place it far away, beyond C, you get a small, upside-down real image. Move it closer to C, and the image grows to the same size. Move it between C and F, and now you have a large upside-down image. But here's where the magic happens. Move the object super close, between the mirror and the focus, and boom! The image flips upright, becomes huge, and is now virtual. This is exactly how a makeup or shaving mirror works. Now, what about our friend the convex mirror? Well, it's way simpler. Doesn't matter where you put the object, close, far, anywhere, a convex mirror will always give you the exact same kind of image, virtual, upright, and smaller. That's it, always. This predictability is what makes them so useful. So I've been throwing around the words real and virtual. Let's make sure we know exactly what they mean. A real image is formed where light rays actually meet up after reflecting. You can literally put a piece of paper there and see the image on it, just like a movie projector. A virtual image, though, is an illusion. It's where the rays only look like they're coming from, behind the mirror. You can't project it on a screen. You can only see it by looking in the mirror. All right, enough with the diagrams and the theory. Let's see how all this physics actually shows up in things you use every single day. And this makes perfect sense, right? Those concave mirrors that can give you that big, magnified virtual image? They're perfect for shaving mirrors or the little mirror a dentist uses.
And the convex mirrors that always give a smaller image but show a huge area? That's exactly what you want for the side view mirror on a car, so you can see more of the road behind you.
And check this out. This is such a cool use of a concave mirror's power. A solar cooker is basically a giant concave mirror that takes all the parallel rays of sunlight from space and focuses them down onto one single tiny point. It concentrates so much energy right there that it can get hot enough to boil water and cook food. It's just pure physics at work.
Okay, you get the concepts. Now for the most important part. How do you get full marks? Consider this your final briefing for absolutely acing this chapter on your exam. First up, the mirror formula. Now don't get scared by the fractions. It's just a really neat equation that links three key things. U, the object's distance, V, the image's distance, and F, the focal length. If you have any two of them, you can always find the third. It's a super powerful tool for solving problems.
Next is magnification, or M. This formula is even simpler. It just tells you how much bigger or smaller the image is compared to the real object. You just divide the image distance V by the object distance U. If M is bigger than 1, the image is magnified. If it's less than 1, it's smaller. Easy.
Now listen up, because this is where students often lose easy marks. Let's talk about the traps to avoid. First, don't mix up which mirror is which, concave versus convex. Second, always remember to describe the image. Is it real or virtual, upright or inverted? And third, be so careful with your plus and minus signs in the formulas. That's called sign convention, and messing it up is the #1 reason people get questions wrong. So what's the game plan? It's simple. Here are your top tips. 1. Memorize those 3 ray rules until you can draw them in your sleep. 2. Practice drawing that whole image table for concave mirrors from memory. And 3. Know your formulas and what every letter means. You do these 3 things, and you are going to be in fantastic shape for the exam.
And let's end on what I call a golden line, a key fact that you should absolutely lock into your brain. Remember this, a concave mirror is special because it's the one that can form both real and virtual images. This chapter is so important for exams, and knowing that one little detail can really make all the difference. Thanks for joining me for this breakdown.
Okay, exam season is hitting hard, and it's time to lock down those marks for chemical reactions and equations. Don't stress, I've got you. Welcome to the only quick guide you're going to need. We're about to cover just the most important stuff to help you absolutely ace this topic.
All right, let's just jump right into it. No fluff, no wasted time. We're focusing only on the core ideas and the skills you absolutely have to know.
And I'm not messing around here. Pay really close attention because what we're covering is pretty much guaranteed to show up on your exam paper. This is essential stuff.
First up, what exactly is a chemical reaction? Well, it's pretty simple, actually. It's just a process where the stuff you start with, the original substances, they change into something totally new. The key thing to remember is you get a new substance with brand new properties. Think about burning paper or when iron rusts. You can't just get that original paper or iron back, right? So, how can you tell if a reaction's happening? Look for these 4 key signs. Does it get hotter or colder? Are there bubbles forming? Did the color change? Or did a solid suddenly appear out of nowhere? If you see any of these, chances are a chemical reaction is going down.
Now, to describe these reactions, we use something called a chemical equation. It's kind of like a recipe. On the left side, you've got your ingredients. We call those the reactants. Then there's an arrow, which shows the reaction taking place. And on the right side, you have what you made, the products. So reactants turn into products. That's it.
But instead of writing out long sentences all the time, we use chemical formulas to be way more specific. For example, calcium oxide plus water makes calcium hydroxide becomes CaO plus H2O gives you CaOH2. See? It's the language of chemistry.
Okay, now for the single most important skill, the one that will absolutely get you marks. Your teacher has probably told you this a million times. You have to balance the equation. But let's quickly talk about why it's such a big deal.
The whole reason is because of a fundamental rule of the universe called the law of conservation of mass. All it means is that you can't just create or destroy atoms during a reaction. Whatever you start with, you have to end with.
And here's what that means for your exam. The number of atoms for every single element has to be the same on both sides of that arrow. If you start with 2 oxygen atoms on the left, you better have 2 oxygen atoms on the right. No exceptions. So, how do we do it? Just follow these 4 steps every single time. First, write down the basic unbalanced equation.
Second, count up the atoms for each element on both sides. Third, add big numbers in front of the formulas. We call those coefficients until the numbers match up. And last, always do a final check to make sure it's all equal.
You know, when you see a reaction like this in a lab, with stuff bubbling and a new solid forming, a balanced equation is the only way to tell the true scientific story of what's happening with all those atoms.
All right, let's practice with a question I can almost promise you'll see. The formation of water. The basic equation is H2 plus O2 gives H2O. Let's balance this thing. Okay, step 2, we count. On the left, we've got 2 hydrogens and 2 oxygens. On the right, 2 hydrogens, but wait, only 1 oxygen? See the problem? The oxygens aren't balanced. This equation is breaking the law. So let's fix it with coefficients. To get 2 oxygens on the right, we'll put a big 2 in front of the H2O. Now we have 2 H2O. But that messes up our hydrogens. We now have 4 on the right. No problem. We just put a 2 in front of the H2 on the left, and there you have it, our final balanced equation. And our final check proves it. 4 hydrogens on the left, 4 on the right. 2 oxygens on the left, 2 on the right. It's perfectly balanced. You've just locked in some serious marks. Next, a super quick bit on energy. If a reaction releases heat and feels hot, it's exothermic. Think of heat exiting. If it absorbs heat and gets cold, it's endothermic. Think of heat going into it. You'll also need to spot different types of reactions. There's combination, where 2 things combine to make one thing. Then there's decomposition, where one thing breaks down into smaller parts. And finally, displacement, where one element comes in and kicks another one out of its spot. Just learn to recognize these patterns. Hey, want to make your answers even better? Add the physical states. An S for solid, L for liquid, G for gas, and AQ for aqueous, which just means it's dissolved in water. These little details can grab you extra credit. And just 2 more quick symbols. An arrow pointing up means a gas is bubbling out. An arrow pointing down means a solid precipitate has formed and sunk to the bottom. Okay, listen closely. This right here is the #1 rule for getting full marks. Do change the big numbers in front, the coefficients. Do not, under any circumstances, change the little numbers in a formula. H2O is water. If you change it to H2O2, that's hydrogen peroxide, a totally different thing. Changing the formula is the biggest mistake you can possibly make. So what's the final takeaway here? It's this. Balancing is not optional. It's not for extra points. If your equation is not balanced, you will lose marks for that question. It's that simple. It is the most critical skill for this chapter. And just like that, we're done. Revision complete. You now have all the key info to crush chemical reactions and equations. Just remember the law, follow the steps, and whatever you do, don't change the formulas. Now go ace that exam. Good luck.
All right, exam time is just around the corner, and you know this chapter is a big one. So let's do a super fast, high-speed revision of acids, bases, and salts to make sure you absolutely ace it.
Seriously, we're going to blast through everything you absolutely need to know in just a couple of minutes. Ready? Let's get that clock started.
Look, we are not wasting any time on the fluffy stuff. This is all about the core concepts, the stuff that is pretty much guaranteed to be on your exam.
Okay, first things first. Let's get right down to the absolute basics. What are we even talking about with acids, bases, and salts? It's actually way simpler than you think. An acid, when you put it in water, it just lets go of hydrogen ions. You know, those little H+ things. And a base? It does pretty much the same thing, but it releases hydroxide ions, or OH- ions. That's it. That's the key difference you've got to lock in. So the obvious question is, what happens if you mix them together? Well, they react, and what you get is a salt. And the most famous salt of all, yep, it's NaCl. Good old table salt. Okay, that's cool, but obviously in the lab you can't just taste stuff to see if it's an acid. So how do you tell them apart? Simple. You use these special things called indicators.
Now pay attention here. This little table, it's your secret weapon, especially for those multiple choice questions. Just memorize these color changes. For litmus, just remember, acid turns it red. And for bases, the big one to know is phenolphthalein. It turns this awesome bright pink. Seriously, burn these facts into your brain.
All right, listen up, because this next part is super important.
I can almost guarantee you're going to see questions on these chemical reactions, so let's make sure we absolutely nail them.
First up, reaction number 1. The rule is, acid plus a metal gives you a salt and hydrogen gas. That's it. A really common mistake here is people forget about the hydrogen gas. Don't be that person. Make sure you write down both products. And here's a perfect picture of it. See this? When a piece of metal, like zinc, gets dropped into acid, you can literally see it happening. Those bubbles are the hydrogen gas being created right there.
Okay, on to reaction number 2. This one is with carbonates. Think of things like baking soda or even crushed up eggshells. Add acid to that, and you get 3 things: a salt, water, and carbon dioxide gas.
And the last big one, reaction number 3, is called neutralization, and this one is huge. It's basically when an acid and a base fight, and they both lose. They cancel each other out, and all that's left is salt and water. This is exactly how antacids work to soothe your stomachache. So, we've got a handle on what acids and bases are, but some acids are way stronger than others, right? So how do we measure that strength? Well, for that, we use something called the pH scale.
Just think of the pH scale like a ruler that goes from 0 to 14. Right in the middle, at 7, that's neutral. Think pure water. Anything below 7 is acidic, and the lower the number, the stronger it is. Anything above 7 is basic, or alkaline. This is a classic exam topic, so please don't get those numbers mixed up.
Okay, so why does pH even matter? Well, because these are your golden ticket examples for those apply your knowledge questions. For instance, did you know that tooth decay kicks in when the pH in your mouth drops below 5.5, and that heartburn you get, that's your stomach acid being too, well, acidic. You take an antacid, which is a base, to neutralize it. See? Real-world stuff.
Okay, here's a bit of a pro tip for you, something that can really set your answer apart. Not all salts are neutral. It all depends on the parents, the acid and base that made it. If you mix a strong acid and a strong base, you get a neutral salt with a pH of 7. But if one is strong and the other is weak, the salt kind of takes on the personality of the stronger one. All right, we're in the home stretch. To wrap things up, let's do a quick fire round of the key compounds you absolutely have to know. First one, baking soda. The formula is NaHCO3. Just remember, it's a mild base, which is why you can use it as an antacid and, of course, for baking.
Next up, washing soda. That's sodium carbonate. And don't forget its formula has that little dot 10H2O attached to it. Its main job? A super powerful cleaning agent.
Then there's bleaching powder, CaOCl2. The name pretty much gives it away. It bleaches stuff. But it also has another really important job, disinfecting water to make it safe to drink. And last but not least, plaster of Paris. The formula is CaSO4.5H2O. You know this stuff. It's what they use to make casts for broken bones because it gets super hard when you mix it with water. Whew, okay, we covered a ton of ground there, and fast. So let's boil it all down. If you're going to remember just 2 things from all of this, what should they be? Honestly, if you're starting to feel a little overwhelmed, just focus on this: the chemical reactions we talked about and the pH scale. Master those 2 concepts, and I promise you are going to be in fantastic shape for your exam. You've totally got this. Good luck.
All right, let's jump right in. Your exams are just around the corner, so we're going to blast through one of the most important topics in physics, refraction at curved surfaces. Get ready for a super fast, high-energy revision session that's going to help you get full marks.
That's the plan. Our mission here is to cover every single essential concept, every golden rule, and every important formula you're going to need from this chapter, all in under 10 minutes. No fluff, just the core stuff you need to absolutely ace your exam.
So before we get all technical, just think about this for a second. What do the glasses you might be wearing and a magnifying glass actually have in common? Well, they both use the exact same principle we're about to break down, bending light through a curved surface to change how we see things.
Okay, let's start at the very beginning. To really get how lenses work, you first have to understand why light even bends in the first place.
It's actually way simpler than it sounds. Refraction is just the fancy word for light bending, and it happens anytime light travels from one substance, say air, into a different one, like water or glass. This change in the medium forces the light to take a little turn. Now check this out. There are really only 2 rules you have to remember for this.
When light goes from a rarer medium like air into a denser one like glass, it bends towards an imaginary line we call the normal. And when it goes back out, from denser to rarer, you guessed it, it bends away from the normal. Simple as that.
To talk about lenses like a pro, we need some key terms. The pole, or P, is just the geometric center of the lens's surface. Easy. The center of curvature, C, is the center of the giant imaginary sphere that the lens was sliced from. And the principal axis, that's the most important one. It's the straight line that runs right through both P and C.
Okay, listen up, because this next part is absolutely critical. If you want to draw any of the diagrams correctly, and you will have to, you need to know these 3 golden rules. They tell you exactly how light behaves when it hits a lens. This is huge for your exam questions.
But hang on, before the rules, let's get one thing straight. A real image is formed where light rays physically cross paths. You could literally put a screen there and see the image. A virtual image is more like an illusion. The light rays only appear to come from a single point. You can see it, but you can't project it.
Rule number 1 is the easiest of all. It's a total freebie. Any ray of light that's traveling perfectly along that main principal axis doesn't bend at all. It just goes straight through like nothing's there.
Rule number 2 is just as easy. The very center of the lens, the optic center, is like a free pass zone. Any light ray that goes through that exact point also goes straight through without bending.
And here's the most powerful rule, the one you'll use constantly. Any ray of light coming in parallel to the principal axis will get bent by the lens, and it's forced to pass through a very special point called the focus, or F. This is the key to finding your image.
So now for the main event. Let's see how we can combine these rules to figure out exactly what kind of image a lens is going to make. This is where those big 8-mark questions are going to come from.
First, let's introduce our 2 main players. A convex lens is thicker in the middle, and its job is to converge light, which just means it brings light rays together. A concave lens is thinner in the middle, and it does the opposite. It diverges light, meaning it spreads the rays apart.
Now, this slide is your absolute cheat sheet for convex lenses. Seriously, go ahead and take a screenshot of this. It tells you everything. Depending on where you put the object, you can get a small image, a same-size image, a big image, or even a virtual one. You have to memorize this table.
And now for the good news. Concave lenses are super simple. They're totally predictable. It doesn't matter where you put the object, a concave lens will always form an image that is virtual, upright, and smaller. Always.
Okay, so you've got the diagrams, which is honestly half the battle. Now for the other half. Let's look at the formulas you need to solve any of the math problems. These are your secret weapons.
This is the big one, the lens formula. It's a simple little equation that connects 3 things: U, the object's distance, V, the image's distance, and F, the lens's focal length. If a question has numbers in it, this is almost definitely where you'll start.
And what if you want to know how big the image is? Just use the magnification formula. It's a simple ratio. Image distance divided by object distance. If M is bigger than 1, the image is magnified. If it's less than 1, it's smaller. That's it.
This one is a little more advanced, but it's really cool. The lens maker's formula explains why a lens has a certain focal length. It connects F to what the lens is made of, that's N, and the curve of its sides, that's R1 and R2. It's the physics behind the lens.
All right, we're almost at the finish line. Let's just do a final check to make sure you are 100% ready to walk into that exam hall and absolutely smash it.
Here's a classic trick question that teachers love to pull. If you take a regular glass lens and you put it underwater, what happens to its focal length? Does it stay the same, or does something change?
Well, it definitely changes. The focal length actually increases. Why? Remember that lens maker's formula? The focal length depends on the refractive index, N, and that value depends on the medium surrounding the lens. So when you go from air to water, the properties of the lens change right along with it. Finally, please watch out for these easy exam traps. Don't lose silly marks. Be extra careful with your plus and minus signs in the formulas. Never, ever forget the 3 golden rules for your diagrams. And please, don't mix up convex and concave lenses. And that is everything. It really just boils down to this. Master the ray diagrams and know your formulas. If you can do those 2 things, you are completely set to score full marks on this topic. You've got this. Good luck. Okay, so exam time is breathing down your neck, right? And you've got to nail one of the most important chapters in physics. Well, don't sweat it. I've totally got your back.
We're about to crush a full revision of the human eye and the colorful world in just about 5 minutes. Ready? Let's jump straight in.
So you've totally done this, right? You're reading something, maybe on your phone, you bring it closer and closer, and bam, the words just go all blurry. It's super annoying. But why does that happen? Well, there's a simple reason, and believe it or not, it all boils down to one very important number.
Yep, that's it. 25 centimeters. That's the magic number. You are definitely going to want to burn this into your brain for the exam because it's pretty much the foundation for understanding how our eyes see up close.
So what is this 25 centimeters? It's what we call the least distance of distinct vision. Just think of it like your eye's personal space. It's comfort zone for reading. If you get any closer than that, the tiny muscles inside your eye that focus the lens just can't keep up. They get strained and everything goes out of focus. So yeah, for a healthy eye, 25 centimeters is the sweet spot.
Okay, so how on earth does our eye even do that? How does it pull off this incredible focusing trick? To get that, we need to take a lightning-fast tour of the eye's main parts.
All right, let's follow the light. First, it zips through the cornea. That's the transparent front window. Then it gets to the iris, you know, the colored part, which acts like a gatekeeper, changing the size of the pupil to control how much light gets in. But the real MVP, the star of the show, is the lens. Its job is to bend that light and focus a perfectly sharp image right onto the retina at the very back. The retina is basically the movie screen of your eye. Now, this next part is super cool. It's a concept called accommodation, and it's basically your eye's superpower. See those tiny muscles around the lens? They can actually squeeze and stretch it, changing its shape. So when you look at something up close, the lens gets thicker. And when you look way out at the horizon, it gets thinner. This constant, tiny adjustment is what lets you switch focus from near to far in a split second. Pretty amazing, right? But, sometimes things go wrong. The system isn't always perfect. And that leads us straight into a huge topic for your exam, vision defects and how we fix them. You're going to want to pay close attention here.
Okay, the two big ones you absolutely have to know are myopia and hypermetropia. And listen, it is so easy to mix these up. So let's make it simple. Myopia, that's nearsightedness. You can see things near you, but stuff far away is blurry. Why? Because the image is forming before it even reaches the retina. On the flip side, you've got hypermetropia, or farsightedness. You can see distant things perfectly, but things up close are blurry. And that's because the image tries to form behind the retina.
So how do we fix this? It's actually pretty logical. For myopia, the light is focusing too early, right? So we need something to spread the light rays out a little before they hit the eye. And that's exactly what a concave lens does. For hypermetropia, the light isn't bending enough to focus on time. So we need a lens to give it an extra push, to bring the light rays together more. And for that, we use a convex lens.
And there's one more you gotta know, presbyopia. This is basically the one that happens as people get older. Those little eye muscles get a bit weak, and the lens isn't as flexible as it used to be. It just makes it really tough to focus on stuff up close. The fix for this? A bifocal lens. It's like having two glasses in one. One part helps you see near, and the other part helps you see far.
So, when you get a prescription for glasses, the number on it is the power of the lens, and we measure it in diopters. The idea is actually super simple. The power is just 1 divided by the focal length. That's it. P equals 1 over F. Now this formula, it is a total classic for numerical questions, so you've got to know it.
All right, we've got the eye down. Now let's shift our focus to the light itself. We're about to get into the really beautiful stuff, light, color, and rainbows. And you can bet this is another topic that's pretty much guaranteed to be on your exam. First up, we have a big word, dispersion. But the idea is simple. You've all seen a prism, right? When white light goes in one side, a rainbow comes out the other. That act of white light splitting into all its different colors, that's dispersion.
And that rainbow of colors always shows up in the same order. We remember it with VibGEOR: violet, indigo, blue, green, yellow, orange, red. But here's the exam critical part. You have to know which one bends the most. Violet light bends the most, while red light bends the least. Just remember that. Violet bends the most, red bends the least.
So where do you actually see this dispersion happening in the real world? Well, the most amazing example is a rainbow. After a rain shower, the air is filled with millions of tiny water droplets. And guess what? Each one of those little droplets acts like a tiny glass prism. So how does this turn into a giant rainbow in the sky? It's a multi-step dance inside every single water drop. First, sunlight enters the drop, and bam, it splits into VIBGR. Second, those colors bounce off the inside back of the droplet. And third, the light comes back out, heading towards your eye. Now imagine millions of raindrops all doing this at the exact same time. And that's how you get a rainbow. Okay, important point here. Do not mix up dispersion with our next idea, which is scattering. They sound similar, but they're totally different. Scattering was what happens when sunlight bumps into all the tiny little particles in our atmosphere, like gas and dust. The light just gets knocked around and sent flying in all directions. It's literally scattered everywhere. And this one simple idea, scattering, explains two huge things. Why is the sky blue? Well, blue light gets scattered super easily by air molecules. So during the day, blue light is just getting bounced all over the place up there, making the whole sky look blue. So then why are sunsets red? At sunset, the sun is low, so its light has to travel through way more atmosphere to get to you. All the blue light gets scattered away long before it reaches your eyes, leaving only the red and orange light to make that final journey straight to you.
Okay, that was a lot, but we've hit all the main ideas. Now it's time for the final stretch. This is your exam game plan, the stuff you absolutely positively have to memorize. Let's do a super fast recap.
First thing, burn this into your memory. Myopia needs a concave lens. Say it with me, myopia, concave.
Next one, the opposite. Hypermetropia needs a convex lens. Hypermetropia, convex. You cannot get these two mixed up. It's a game changer.
And speaking of mixing things up, let's talk about the most common mistakes people make. Number 1, getting the lenses for myopia and hypermetropia backward. Don't do it! Number 2, forgetting that 25 centimeter number. It's an easy mark to get. And finally, confusing dispersion with scattering. Remember, dispersion is splitting light, scattering is bouncing light.
Look, here's the bottom line. It all comes down to 3 things. If you can walk into that exam hall knowing your vision defects, dispersion, and scattering, you are going to ace this section. I promise. You've got this. Now go crush that exam.
All right, your exam's just around the corner, and you've got to nail the structure of the atom like yesterday. Well, you've come to the right place. Let's get right into this super fast exam cram. Okay, so here's the deal. We're going to blitz through the entire atom chapter in basically no time. We're only hitting the absolute must-know stuff, the things that are guaranteed to come up. So get ready to lock in. And I'm not kidding, you really need to pay attention here. The stuff we're about to cover, this is what's going to be on your exam. Think of this as your cheat sheet for getting those top marks.
So where do we even start? Believe it or not, with light. Yeah, it sounds a little weird, right? But that rainbow you see after it rains, that's actually one of the biggest clues we have for figuring out what's going on deep inside an atom. I mean, we've all seen a rainbow, that classic band of colors, Vibgyor, violet, indigo, blue, and so on. Well, that's what scientists call the visible spectrum. It's just white light broken down into all its different color components. So light actually travels as a wave. And that brings us to our very first absolutely must-know formula. It's C equals lambda nu. So what does that mean? C is the speed of light. It's a constant. That's equal to its wavelength, that's lambda, multiplied by its frequency, which is nu. This rule applies everywhere, all the time. Okay, now this is where it gets really cool. A guy named Max Planck had this huge idea. He said, hey, what if energy doesn't just flow smoothly, like water from a tap? Instead, he figured it comes in these little individual packets. He called them quanta. And that idea leads us straight to our second critical formula, E equals each nu. Basically, the energy, E, of one of those little packets of light is directly connected to its frequency, nu. And the takeaway here is super simple. If the frequency is high, the energy is high. That's it. And here's a perfect example. Think about blue light. It has a really high frequency, so you guessed it, high energy. And red light, it has a low frequency, which means low energy. See? Simple. All right, so we've talked about light and energy packets, but how does any of this relate to atoms? Well, that's where Niels Bohr comes in. He created the first really useful map of the atom, and it's simple, but wow, it was powerful. So Bohr's model boils down to 3 main ideas. First, he said electrons move in these fixed circular paths around the nucleus, kind of like planets orbiting the sun. Second, each of these paths or orbits has its own specific energy level that doesn't change.
And third, the orbit that's closest to the center, that's the one with the lowest energy, and we call that the ground state. Okay, and here it is. This is the big connection back to light. When an electron soaks up some energy, it gets excited and jumps up to a higher orbit. But it's unstable up there. It can't stay for long. So when it falls back down to its original spot, it has to release that extra energy. And it does that by spitting out a packet of light. That's the light that creates those lines in a spectrum.
Look, Bohr's model was a genius idea for its time, a huge step forward. But it wasn't the whole story. We needed a more accurate map. So let's jump to the modern version, the quantum model, and see how it leveled up from Bohr's ideas. This right here is probably the single biggest, most important difference you have to know. We throw out that old idea of a fixed orbit. It's outdated. Instead, we talk about an orbital. And what's an orbital? It's a 3D cloud of probability. It's the region where you're most likely to find the electron. Getting this difference right is absolutely critical for your exam. Okay, so if electrons are just buzzing around in these fuzzy clouds, how on earth do we pinpoint one? Well, we can't know exactly where it is, but we can give it an address. And this address is made up of 4 special codes, which we call quantum numbers. Let's break down that address. First, you have N, the principal quantum number. Think of that as the state, or a big city. It tells you the main energy level, or shell. Then you have L, which tells you the shape of the orbital, whether it's an S, P, D, or F. Next is ML, the magnetic one. That's the house number. It tells you which way the orbital is pointing. And finally, MS, the spin. That tells you if the electron is spin up or spin down. And here's what those shapes actually look like. An S orbital is just a simple sphere. Easy enough. But P orbitals look more like dumbbells. And remember that ML number? That just tells us if the dumbbell is lying along the x-axis, the y-axis, or the z-axis. It's all right there in the quantum numbers. Okay, great. We have the address system for electrons. But now, how do we actually start placing electrons into these orbitals? How do we fill up the house? Well, it turns out there are 3 really simple rules you just have to memorize. These are the 3 golden rules. Rule number 1 is the off-bow principle. It's simple. You always fill the lowest energy orbitals first. Start from the ground floor and work your way up. Rule 2, the Pauli exclusion principle. This says each orbital can only hold a maximum of 2 electrons. And if you have 2, they have to have opposite spins. And finally, Rule 3, Hund's rule. This one's important. If you have a set of orbitals with the same energy, you have to put 1 electron in each one before you go back and start pairing them up. All right, that was a lot, but we've hit all the main ideas. Now it's time for a super quick-fire review to make sure this all sticks. This is your last-minute cram, your ultimate cheat sheet for the exam. Okay, you need to burn these into your brain. The formulas, C equals lambda nu and E equals h nu. Got it? Next, the maximum number of electrons you can fit in any given energy shell is 2n squared. And finally, the max electrons for each subshell. S gets 2, P gets 6, D gets 10, and F gets 14. Just memorize those numbers. Now here's a super common mistake. Please, please, please do not get these mixed up. An orbit is the old, outdated idea of a flat path. An orbital is the correct, modern idea of a 3D probability cloud. Orbit is wrong, orbital is right. And the other big mistake people make all the time? Forgetting Hund's rule. Remember, when you're filling up those p orbitals or d orbitals, you put 1 electron in each box first. Don't start making pairs until every box has 1 electron in it. Spread them out before you pair them up.
And that's a wrap. Just like that, we've covered the whole thing. The spectrum, Bohr's model, the quantum model, all 4 quantum numbers, and the 3 rules for filling orbitals. Your super fast revision is officially done.
So here's the bottom line. If you can walk into that exam and you know the quantum numbers, you know the 3 rules, and you know those 2 simple formulas, you're setting yourself up for full marks. It all boils down to that. Now go crush that exam.
All right, hey everyone, exams are right around the corner, so we're going to tackle one of the most important topics in chemistry. Get ready for a super fast, high-energy revision of the entire periodic table. Let's just dive right in. So our goal here is pretty simple. We're going to cover everything you absolutely need to know about the periodic table, from its history all the way to its trends, in like the next 5 minutes. It's perfect for that last-minute study session to really lock in those full marks. You know, just imagine walking into a huge pharmacy to find one specific medicine, but everything is just thrown on the shelves randomly. It'd be impossible, right? Well, that's kind of the problem scientists had with all the elements. They desperately needed a system, a way to classify everything to make it make sense. And that challenge, well, it led to one of the greatest achievements in all of science.
So, where did this all start? This massive organization project? It all began with a hunt for some kind of hidden pattern among the elements. Let's check out the first few attempts.
Okay, so the first real clue popped up way back in 1829 from a guy named Johann Wolfgang Dobereiner. He started noticing that you could group certain elements into threes, and he called them triads. And here was the really cool part, the key insight. The atomic weight of the element in the middle was almost the perfect average of the other two. Kinda neat, right?
So yeah, the big win for him was proving there was some kind of link between an element's atomic weight and its properties. But, and here's the catch, this is what you need to remember for your exam. It was super limited. It only worked for a handful of element groups. Its key failure was that it just wasn't a universal law.
All right, fast forward a bit to 1865, and John Newlands comes along with a pretty musical idea. He arranged the elements by their atomic weight and discovered that properties seemed to repeat with every 8th element, just like notes on a musical scale. You know, do, re, mi, fa, sol, la, ti. And boom, you're back at a do with similar properties.
So, what Newlands really nailed was this idea of periodicity, the idea that properties repeat in a predictable pattern. And that was a huge step forward. The problem was his system kind of fell apart once you got to the heavier elements, and sometimes it would force elements that were totally different into the same group, which, just didn't make any sense.
So these first tries were good, but they weren't the whole story. The world was kind of waiting for a real genius to connect all the dots. And that genius was Dmitri Mendeleev. This is a name you absolutely, positively have to remember.
And here he is, the man himself. See, Mendeleev wasn't just sorting elements. He felt like he was uncovering a fundamental law of nature. His periodic table was a total game changer, and it's basically the foundation of the one we still use today. So what was Mendeleev's secret sauce? What made his table so brilliant? Well, he used atomic weight, sure, and he grouped similar elements together. But here's the stroke of genius. He was so confident in his pattern that he left empty spaces, gaps for elements that hadn't even been discovered yet. He even predicted what they would be like an element he called Eka aluminum. And guess what? When we found it years later, we call it gallium. His predictions were spot on. Just incredible.
Okay, but it wasn't perfect. Its biggest weakness was something we call the anomalous pair problem. See, to keep elements with similar properties in the right columns, he sometimes had to break his own rule of increasing atomic weight. The classic example you gotta know is tellurium and iodine. I mean, check out their weights. He had to put the heavier one before the lighter one. That told everyone that atomic weight wasn't quite the right answer.
So that little problem, that final piece of the puzzle that would fix Mendeleev's table, it came from finally understanding the structure of the atom itself. And this led to the modern table that we all know and, well, that we all have to study.
And this brings us to the golden rule, the modern periodic law.
A scientist named H.J. Moseley figured out that the true fundamental organizing principle wasn't atomic weight at all. No, it was the atomic number. The number of protons an atom has. That was the property that governed everything.
Okay, so if there's one thing you take away from all this history, it's this. Mendeleev used atomic weight. The modern table uses atomic number. That single change, as you can see right here, fixed everything. All the old problems like that tellurium iodine issue just disappeared.
And this is what we get, the modern periodic table, perfectly organized by atomic number. Its whole structure is built on 18 vertical columns we call groups and 7 horizontal rows we call periods. And the key is elements in the same group share similar chemical properties, like the superreactive alkali metals in group 1 or the really chill noble gases over in group 18. Now, we can also slice up the table into what we call blocks, and this is all based on their electron configurations. You've got the S block over on the left, the P block on the right, the D block smack in the middle, and those F block elements that are kind of pulled out at the bottom.
All right, let's get to the really, really important part for your exams. This is about actually using the table to predict how elements behave. These are the periodic trends, so pay close attention.
First up, atomic radius. And yeah, it's pretty much what it sounds like. It's just the size of an atom. Simple enough. But the key question is, how does that size change as we move around the table?
Well, as you can see, when you move from left to right across a period, the atoms actually get smaller. Now, that might seem weird, but think about it. You're adding more protons to the nucleus, so that stronger positive charge pulls all the electron shells in just a little bit tighter. But when you go down a group, the radius gets bigger because you're adding whole new layers of electrons. So just remember, down gets bigger, across gets smaller.
Okay, trend number 2, ionization energy. All this is the amount of energy you need to yank an electron away from an atom. You can just think of it as how tightly an atom holds on to its outermost electrons.
And the trend here is basically the reverse of atomic size. As you go across a period, the atoms get smaller and hold their electrons tighter, so it takes more energy to remove one. Ionization energy increases. As you go down a group, those outer electrons are further away and easier to snatch, so the energy needed decreases. And that right there is why the metals on the far left are so crazy reactive. It takes almost no energy to give away that electron.
Last but not least, let's talk about metallic character. Just look at the table. Where are the metals? They're mostly on the left side and towards the bottom, right? So it makes perfect sense that an element's metallic character, its tendency to lose electrons, increases as you go down a group and decreases as you go across a period. And non-metallic character, well, that's just the exact opposite.
Okay, before we wrap this up, let's talk about some super common mistakes you really want to avoid so you don't lose easy marks. First, do not ever mix up atomic number and atomic mass. Second, double-check the direction of the trends. It's so easy to mix them up. And finally, just be careful and precise when you're writing down group and period numbers.
So what's the ultimate takeaway here? Honestly, if you can master the periodic trends, really understand the structure of the modern table, and know your key groups, you are absolutely golden. You're gonna ace this. You've got it. Good luck.
All right, exam season is upon us, and today we're jumping into a huge topic in chemistry, chemical bonding. Let's cut right to the chase and get you everything you need to know.
So, here's the game plan. A super fast, no-fluff revision of the whole chapter. We're skipping the long, boring lectures and hitting only the most important must-know points. Let's do this.
You ever stop and think about that? I mean, why is the salt on your table a bunch of tiny hard crystals, while the air you're breathing is a gas and water is a liquid? It seems kind of random, right? Well, it's not. There's a really specific reason behind it. And here's the big secret. It all boils down to these invisible forces that basically glue atoms together. We call them chemical bonds. The kind of bond and how strong it is decides pretty much everything about a substance. Okay, but why do atoms even link up in the first place? Well, it's all about one simple driving force. They're all on a quest to become stable. See, unstable atoms are antsy and reactive, and they will do just about anything to find that stability.
And that leads us to our first key definition. A chemical bond is just that force of attraction. It's the cosmic superglue that takes all these individual, chaotic atoms and organizes them into the stable stuff that makes up our world.
So we know atoms want to be stable, but how? How do they actually do it? This is where a very, very special number comes into play. You could almost call it the secret code for understanding chemistry.
Now, before we get to that magic number, let's meet the key players, the valence electrons. Think of them as the electrons on the outer edge of an atom. They're the only ones that actually get involved in the action of bonding.
And here it is, 8. This is it. This is the number that basically runs the entire world of chemical bonding. It's the goal. It's the finish line that most atoms are desperately trying to reach.
And I really want you to lock this in. If you can just remember this one number, you've pretty much figured out why most chemical reactions happen in the first place. Atoms are all trying to get to 8 valence electrons.
This brings us to the single most important rule in this chapter, the octet rule. It's simple. It just says that atoms will either give away, take, or share their electrons to end up with a full outer shell of 8. Why? Because that configuration is super stable, just like the noble gases, the cool kids of the periodic table.
So how do these atoms hit that magic number 8? Well, the first strategy is pretty straightforward. One atom just gives its electrons away, and another atom takes them. This little exchange usually happens between a metal and a non-metal. Metals are the givers. They like to lose their few valence electrons, which makes them become positively charged. We call those cations. Non-metals are the takers. They're so close to a full shell, so they grab electrons and become negatively charged anions. Let's go back to our salt example. NaCl. You've got sodium, a metal, with one valence electron it's just dying to get rid of. Then you have chlorine, a nonmetal, with 7. It wants one more so badly. So sodium just transfers its electron over to chlorine. Now, sodium is positive, chlorine is negative, and boom, opposites attract. That powerful attraction is the ionic bond.
And that super strong attraction is why salt is the way it is. Ionic compounds form these hard, crystalline solids, and they have crazy high melting points. Oh, and because they're made of charged particles, they can conduct electricity, but only when you dissolve them in water. It's all connected back to that bond.
Okay, but what if you have two atoms and they both want to gain electrons, right? Neither one is going to just give any up. So what do? They turn to strategy number 2. They form a partnership. They agree to share.
And this, my friends, is a covalent bond. It usually happens between two nonmetals. Instead of one giving and one taking, they put their electrons in the middle and share them. That way, each atom gets to count the shared electrons toward its own octet. It's a total win-win situation.
Let's take the oxygen we breathe, O2. Each oxygen atom has 6 valence electrons, so it needs 2 more. To solve this, 2 oxygen atoms come together and share 2 pairs of electrons. That's 4 electrons in total. We call this a double bond, and just like that, each oxygen atom gets to have its full octet.
And we can push this even further. Look at nitrogen, N2. Each nitrogen atom needs 3 electrons, so what do? They share 3 pairs between them. This is called a triple bond, and it is incredibly strong, which explains why nitrogen gas is so stable and doesn't like to react with much.
Okay, so we've got our 2 main ways atoms can bond, but here's where it gets really cool. Bonding doesn't just stick atoms together. It actually gives molecules their specific 3D shape, and that shape is everything when it comes to how they work.
So how does a molecule get its shape? It's all because of a really simple idea called VSEPR theory. The main point is this. All the electron groups around the center of an atom are negative, right? So they push away from each other. To get as far apart as possible, they arrange themselves in 3D space, and this creates predictable shapes. This pushing and shoving leads to some really common geometric shapes. For instance, if you have 2 electron groups, they're going to push each other to opposite sides, forming a straight line. That's a linear shape. With 3 groups, they spread out into a flat triangle. And with 4, they form a 3D pyramid shape called a tetrahedron. It's just about giving each other space.
All right, let's lock all this information in. It's time for a lightning round review of the most important points you absolutely need for your exam. This is it, so listen closely.
Okay, this is the big one, the difference between the 2 main bond types. Ionic bonds involve a transfer of electrons. It happens between a metal and a nonmetal. Covalent bonds involve sharing electrons, and that happens between 2 nonmetals. If you get this, you are golden.
And look at what this means for the real world. The difference in properties is just staggering. That strong ionic bond in salt gives it a melting point of over 800 degrees Celsius. Meanwhile, a covalent compound like ethane is a gas way, way below freezing. The type of bond really does control everything.
I'm telling you, this is the #1 trap students fall into. They mix up ionic and covalent. Just burn this into your brain. Ionic is a transfer, a giveaway. Covalent is sharing like coworkers. Don't let this simple mistake cost you points.
And that's really the whole story. If you can confidently explain the octet rule, tell the difference between ionic and covalent bonds, and describe how VSEPR theory creates molecular shapes, you've totally nailed the core of this chapter. You're ready. Go get 'em.
All right, exam season is on, and you need a super fast, super effective revision of electric current. Well, that's exactly what we're going to do. In just the next few minutes, we're going to smash through the essential formulas and concepts that you absolutely have to know. Let's get right into it. And listen, I am not kidding. The stuff we're about to cover, these are the greatest hits, the most important questions that show up on the exam again and again. So really focus, because this is pretty much your ticket to acing this chapter.
So here it is. This is our secret weapon, our entire strategy boiled down to one single line. If you can just master these 4 things, the main formulas, how series and parallel circuits work, and the king of them all, Ohm's law, you are golden. Think of this as our roadmap to full marks.
Okay, let's dive in, starting with the absolute basics. You can't build a house without a solid foundation, right? Well, you can't solve circuit problems without knowing these 3 key players inside and out.
First up is electric current, which we always call I. And honestly, don't overthink this one.
Just imagine water flowing through a garden hose. Electric current is basically the same thing, but instead of water, it's a flow of tiny electric charges, usually electrons, moving through a wire. It's all about the movement.
And here is the very first formula you need to burn into your brain. Current, which is I, is just the amount of charge, that's Q, that flows past a certain point, divided by the time, T, it took to do it. So how much charge per second? Simple. And the unit we use for this is the ampere.
So what's actually going on inside that wire? Well, without a battery, the electrons are just a chaotic mess, bouncing around all over the place with no direction. But the second you connect a battery, it acts like a traffic cop. It gives them a push and gets them all marching in one single organized direction. That organized march, that is your electric current. Now, that push we keep talking about, it has a proper name, potential difference. You probably know it as voltage. It's basically the electrical pressure in a circuit. If you don't have any voltage, those charges have no reason to move, and you get zero current. No push, no flow.
And of course, it has a formula. Voltage, V, is the amount of work done, W, or energy, for each unit of charge, Q. It tells you exactly how much energy each little charge gets to make its journey around the circuit.
And finally, we have resistance, which we call R. So if voltage is the push, then resistance is kind of like friction. It's whatever is opposing that flow of current. And you know, a longer wire will have more resistance. A thicker wire? Actually less resistance. And for most things, if the wire gets hotter, the resistance goes up too. We measure it in a unit called the ohm.
So we've got the push, that's voltage. We've got the flow, that's current. And we've got the friction, that's resistance. Now it's time for the master rule that connects them all. This is, hands down, the most important part of this entire chapter.
Seriously, if you could only take one single formula into the exam with you, what would it be? It's the one that ties voltage, current, and resistance all together.
Boom. V equals I times R. This is Ohm's law. It is the king of all circuit formulas. It just tells us that the push you apply is directly connected to the flow you get and the friction in the wire. You have to memorize this. It is your best friend for solving almost any problem.
So let's just quickly break that down. First, V is directly proportional to I. That means if you double the push, you double the flow. Simple. That's why if you graph it, you get a perfect straight line. But, and this is so important, it's the detail that separates the good answers from the great ones. Ohm's law only works if the temperature doesn't change. They love asking about this little catch.
Okay, we've got the basics down, and we have the master rule. Now for the last two pillars, how we actually connect things together. There are really only two ways you need to know, series and parallel. And you absolutely have to know the difference. This slide is perfect. Just look at the key differences. In a series circuit, everything is in one line, a single path. So the current has to be the same everywhere. But in parallel, the path splits up into branches. So the voltage, the push, is the same across every single branch. And check out the formulas for resistance. They're completely different. For series, you just add them up. Easy. For parallel, you have to do that 1/R thing. And here's what they actually look like. Over on the left, that's series. See, the current has only one way to go, straight through all three bulbs. But on the right, that's parallel. The current gets to the junction and it splits. This is exactly why the lights in your house are wired in parallel. If one bulb blows, the others don't care. They stay on. Makes sense, right?
Awesome. Let's quickly put this all together with two final really practical ideas. Power, which is how we measure the energy being used, and a quick bit on safety. Electric power, or P, is just how fast a device is using energy. The main formula couldn't be simpler. Power equals voltage times current. P equals VI. But here's a pro tip. If you mix this with Ohm's law, you can get two other super useful versions. P equals I squared R and P equals V squared over R. Knowing all three gives you a massive advantage. Okay, let's talk safety. What happens if you plug too many things into one outlet? All those devices try to pull a huge amount of current. That's called overloading. The wires in the wall can get super hot, and that's dangerous. So what's the solution? A simple little thing called a fuse. A fuse is just a special piece of wire that's designed to be a weak link. If the current gets too high, the fuse literally melts, breaking the circuit and stopping the electricity. It sacrifices itself to save everything else. Okay, you have all the knowledge. Now let's make sure it's locked in. Time for a quick rapid-fire round to get these core ideas stuck in your brain for exam day. You ready? First question, nice and easy. What is the unit of electric current? Go. The answer is ampere. Of course it is. And quick follow-up, in a parallel circuit, what stays the same across all the branches? Voltage. That's right. The push is the same on every path. And please don't forget to write your units in the exam. All right, last thing, let's go over the common mistakes that trip people up. Try to avoid these. Number 1, don't mix up voltage, the push, with current, the flow. They are not the same thing. 2, always double check if you're using the right resistance formula for series or parallel. 3, write down your units. It's such an easy way to get points. And finally, don't forget that little detail about Ohm's law and constant temperature. And that is a wrap. You've just done a complete blitz through the absolute core of electric current. Seriously, if you just focus on those 4 pillars, the formulas, series, parallel, and Ohm's law, you are going to be in a fantastic position. You have all the tools you need. Now go into that exam with confidence. You've got this. All right, exam season is here, and it's time to absolutely nail electromagnetism. In just the next few minutes, we're going to blitz through the core concepts that are guaranteed to earn you marks. No fluff, just the stuff you need to know. Let's dive in.
And I'm not kidding, the things we're about to cover, they show up on exams, like all the time. This isn't just theory for the sake of theory. This is your cheat sheet for understanding the questions that really matter. So, let's get focused.
First things first, you've got to understand that electromagnetism is a two-way street. We're going to start with the first direction, how a simple flow of electricity can, like magic, create a magnetic field right out of thin air. So our story kicks off way back in 1820 with a guy named Hans Christian Ørsted. He's in the middle of a lecture, passes an electric current through a wire, and bam! A compass needle nearby just moves. That was the aha moment. He proved that electricity and magnetism weren't two separate things, but were actually deeply connected. So what exactly did that current create? Well, it created a magnetic field. Think of it as an invisible bubble of influence, a force field. It's kind of like gravity, right? You can't see it, but you can for sure feel its effects. And it's this field that pushes and pulls on other magnets or, as we'll see, moving charges. Okay, so if this field is totally invisible, how in the world are we supposed to draw it or understand it for an exam question? How can we actually see its direction and its strength? Let's break it down. We use something called magnetic field lines. Now, the most important rule on this line, the one you absolutely have to remember, is this. Where the lines are all bunched up and crowded, the field is super strong. Where they're spread out, the field is weak. Simple, right? Density equals strength. That's a classic exam question right there.
So how do we know which way those lines are supposed to go? Well, this brings us to your first essential tool, one of our big 3 for this whole explainer. It's the right-hand thumb rule. You literally have to know this to get those direction-based problems correct.
And you know what? It couldn't be easier. Seriously, do it with me now. Take your right hand, point your thumb in the same direction the current is flowing. Now, look at how your fingers naturally curl around. Yep, that's it. That's the direction of the magnetic field. Do it a couple of times and it's locked in forever. So what if we take that straight wire and we bend it into a loop? Well, something cool happens. All those magnetic field lines get concentrated right through the middle of the loop. We're basically starting to build a much stronger, more focused magnet. And hey, if one loop is good, then a whole bunch of loops must be even better, right? Exactly. When you wind a wire into a tight coil like this, you get what's called a solenoid. This thing creates a really strong, and this is important, a very uniform magnetic field inside. It behaves just like a regular bar magnet. This is the secret behind things like junkyard cranes and even the starter in a car. Okay, so we know how to make magnetic fields. Now for the really fun part. We're going to use these fields to actually create forces and make things move. This, right here, is the core idea behind every single electric motor on the planet. Now, this is the key. A magnetic field only pushes or pulls on an electric charge if that charge is actually moving. A charge just sitting there feels absolutely nothing. It's all about the motion. Motion is the magic ingredient. Now for the math part. Here's the formula you'll need. The force, F, depends on the charge, Q, how fast it's going, V, and how strong the magnetic field, B, is. But here's the main takeaway. You get the biggest possible force when the charge moves at a perfect right angle to the field. And let's think about it. What is an electric current, really? It's just a whole bunch of charges all moving together. So it makes perfect sense that if a single moving charge feels a force, a wire that's carrying a current is going to feel that force too.
And here it is. This is the workhorse formula for your exam. F equals ILB. Force equals the current times the length of the wire in the field times the field strength. You got to memorize this one. It's for that perfect situation when the wire is perpendicular to the field, which luckily for us, it usually is in exam questions. So all of this leads us to our second big three topic, the electric motor. This amazing gadget uses that exact magnetic force on a coil of wire to turn electrical energy into useful mechanical energy, the spinning motion that drives everything from a blender to an electric car. All right, let's flip the script. Time to head to the other side of our two-way street. We've used electricity to make magnets and motion, but what about the other way around? How can we use magnetism to create electricity? This whole idea is called electromagnetic induction. And the key word you have to remember here is change. You can't just let a wire sit in a magnetic field and expect something to happen. No way. You need relative motion. Either the wire has to move or the magnet has to move. It's this change that actually creates the current. And this is all described by our final big three concept, Faraday's law. All it's really saying is that the voltage you create depends on how fast you change the magnetic field passing through your coil. So, what's the takeaway? A faster change means a bigger current. Simple as that. So which way does this new current flow? Lenz's law has the answer. The new current will create its very own magnetic field that actually fights back against the change that created it in the first place. It's kind of like nature's way of saying, I don't like change. Okay, let's tackle one of the most common mistakes students make on the exam. It is so easy to get these two mixed up when you're under pressure, but after this, you won't. Motor versus generator. Let's solve this mystery once and for all. Just look at this slide. It's all about what goes in and what comes out. A motor takes electricity in to create motion out. A generator is the total opposite. You put motion in, like wind spinning a turbine, to get electricity out. They are literally the reverse of each other. And there you have it. This is your final checklist for getting full marks. Number 1, the right-hand rule for figuring out the direction of the field. Number 2, the electric motor principle, which explains how force creates spinning motion. And number 3, Faraday's law, which tells us how changing fields create a current. So let's end on this. If you can walk into that exam and confidently explain the motor, Faraday's law, and the right-hand rule, you are in amazing shape. You are ready for a top score. You've got this. Good luck.
All right, exams are right around the corner, and you need to lock in the key concepts of metallurgy, and fast. Well, you've come to the right place. This is your super fast revision to make sure you're totally ready. Okay, let's jump right in. And I'm not kidding about this. Everything we're going to cover in the next 10 minutes is the stuff that shows up on tests all the time. So pay close attention, and you'll be all set to crush those questions. First things first, we've got to speak the language. Understanding these 4 key terms is a must, because they're the foundation for literally everything else. So let's get these down. Okay, so a mineral. What is it? Super simple. It's just the raw form. Think of it as any compound you can find in the Earth's crust that has a metal in it. That's it. It's our starting point. Now, here's where it gets interesting. An ore is a special kind of mineral. The key word here is profitably. It has to have enough metal in it to make all the digging and processing actually worth the money. It's all about the economics. So when you dig up an ore, it's not going to be clean. Nope. It's mixed with a ton of useless junk. Sand, dirt, little rocks. That junk has a name, and it's called gangue. And our first job is always to get rid of it. Okay, so how do we get rid of that gangue? We add something called a flux. You can think of a flux as a chemical cleaner. It reacts with all that junk, turning it into a lightweight, melty waste that we can just skim right off the top. Easy. So let's nail this down, because it's a classic exam trap. All ores are minerals, but not every single mineral is an ore, right? If you find a rock with a tiny fleck of gold, that's a mineral. If you find a rock that's loaded with enough gold to make you rich, now that's an ore. Do not mix these up. All right, let's get to what I think is the single most important idea in all of metallurgy. If you get the reactivity series, you pretty much have the cheat code for how to extract any metal.
And here it is. Up at the top, you've got your super reactive metals like potassium and aluminum. In the middle, you've got your kind of reactive guys like zinc and iron. And way down at the bottom, you find the least reactive ones like gold and silver. These guys are so chill, they're often found just as pure metal.
So you're probably thinking, okay, great, a list, why should I care? It's a fair question. Why do we even bother memorizing this order? What's the big deal?
Well, here's the big deal. A metal's spot on this list tells you the entire game plan for getting it out of its ore. See, the more reactive a metal is, the tighter it holds on inside its compound, and the more energy you need to break it free. You can't treat aluminum like you treat gold, and this list tells you exactly why. Now that we've got the lingo and the main rulebook down, let's look at the overall process. The whole thing, all of metallurgy, can be broken down into a simple, logical, three-step journey, from a dirty rock to a pure, shiny metal. Step 1 is concentration. This is where we clean the ore and get rid of all that gang. Step 2 is extraction. We do some chemistry to get the raw, kind of dirty metal out. And step 3 is refining. We purify that crude metal to make it really, really pure. So just remember, clean it, extract it, and purify it. That's the master plan. Okay, let's zoom in on the juicy details now. These are the specific processes and reactions you absolutely have to know. Trust me, these are the ones that show up as big mark questions on the exam. So for concentration, we use pretty simple physical methods. Handpicking is, well, exactly what it sounds like. Washing is basically like panning for gold. The heavy ore sinks and the lighter junk washes away. Froth flotation is super clever. It's mainly for sulfide ores, where the ore sticks to oily bubbles in a froth. And magnetic separation is a no-brainer. Use a magnet when either the ore or the gangue is magnetic. Oh, this is another one people always get mixed up, roasting and calcination. They both involve a lot of heat, but the difference is so important. Roasting is done with lots of air, and it's usually for sulfide ores. Calcination is done without air for carbonate ores. Here's a little trick. Roasting has an A in it, for air. And here is where that reactivity series we talked about really pays off. It all makes sense now. Your highly reactive metals are so stubborn, you need to blast them apart with a ton of electricity. That's electrolysis. The medium guys can be coaxed out with a chemical reaction called reduction, usually with carbon. And the least reactive metals, they're so weakly bonded that just heating them up is usually enough. Now for something really cool and powerful, the thermite process. What we do is we take aluminum, which is more reactive than iron, and use it to literally steal the oxygen away from iron oxide. And this reaction gives off a crazy amount of heat, so much heat that the iron it produces is instantly melted. So what's the point of all that intense heat? Well, it has a really important job: welding. That molten iron from the thermite reaction is perfect for joining together huge pieces of steel, like railway tracks, right there on the spot. It's some seriously powerful chemistry in action. Okay, for our last big step, refining. The most important method is electrolytic refining. So here's the setup. We take our big, impure slab of metal and make it the positive anode. A super thin, pure strip is our negative cathode. We pass a current and the pure metal atoms actually dissolve from the impure slab, travel through the liquid, and plate themselves onto the pure cathode, building it up layer by perfect layer. All the junk just falls to the bottom as something called anode mud. So, we did it. We extracted and purified our metal. But the story isn't quite over. See, nature wants to turn that shiny metal back into a compound. We have to protect it. Let's talk about corrosion. The number one example of corrosion is, of course, the rusting of iron. And the most important thing you have to remember is this. For rust to happen, you need two things at the same time. You need air, specifically oxygen, and you need water. If you take away just one of them, the iron will not rust. Period. So, preventing rust is all about stopping the air and water from touching the metal. You can paint it to create a physical barrier, you can electroplate it, coat it with another metal, or you can change the metal itself by making an alloy like stainless steel, which is just naturally good at resisting rust. And that's a wrap. Mineral versus ore, the reactivity series, the three big steps, those key reactions like roasting and calcination and corrosion. You've just reviewed the absolute heart of metallurgy. You totally got this. Now go in there and get those full marks.
All right, future toppers, exams are just around the corner, right? So let's do a super quick, power-packed revision of one of the most important chapters you're going to face, carbon and its compounds. Let's just jump right in.
Just think about this for a second. Agar carbon nahi hota, to life bhi nahi hoti. No, seriously. Without carbon, life as we know it, well, it just wouldn't exist. The food you eat, the clothes you're wearing right now, even the fuel that runs our cars, it's all carbon, man. It's everywhere.
So, what's the big deal with carbon? Why do we call it the king of elements? Let's get right into its basic properties, because trust me, if you get this part, the whole chapter becomes a piece of cake.
Okay, let's get into the basics. Carbon's atomic number is 6. You know what that means? Its electronic configuration gives it 4. Count them. 4 electrons in its outermost shell. And these, my friends, are the valence electrons. Now this number 4 is the whole secret. Think about it. Losing all 4 electrons? Nah, that takes way too much energy. Gaining 4 more? Super difficult. So, what's a carbon atom gonna do?
It does what we all do with our friends. It shares. Carbon shares its electrons. And this whole sharing business is what we call covalent bonding. It's just like sharing your tiffin, right? You don't give the whole thing away, and you don't snatch someone else's. You share, and you make a strong, stable friendship. In chemistry, that friendship is a covalent bond. As simple as that. Okay, so covalent bonding is its basic nature. But what makes carbon a total superhero in the world of elements? Well, it's got 2 incredible superpowers, and you have got to remember these for your exams. These are game changers.
First up, superpower number 1, tetravalency. Just break down the word. Tetra means 4. Valency is 4. It means one single carbon atom can form 4 separate bonds. It's like it has 4 hands, reaching out to connect with other atoms all around it. This is how it builds these huge, complex 3D structures.
And then there's superpower number 2, catenation. Now this one is really special. It's the unique ability of carbon to form strong bonds with other carbon atoms. It's like they're holding hands with each other, forming these long, unbreakable, what do we call them? Dosticky chains. These friendship chains can be long and straight, they can have branches, or they can even form rings. Amazing, right?
Listen up, because this slide is everything. This is the core mantra of this whole chapter. If they ask you, why does carbon form millions of compounds? This is your answer. It's because of its 2 superpowers: tetravalency, the ability to form 4 bonds, and catenation, the ability to form long chains with itself. That's it. This is the golden answer you need to write in your exam. Burn this into your brain.
And just look at what this leads to. Because of these amazing superpowers, carbon can exist in all these different forms, which we call allotropes. You know about diamond and graphite, of course, but check out this crazy football-shaped molecule. That's Buckminster fullerene. It's all just carbon, but the structure is completely different. So cool.
All right, let's move on to the simplest family of carbon compounds. What happens when carbon only bonds with hydrogen? Well, you get hydrocarbons. And this right here is basically the starting point for all of organic chemistry.
Okay, this table is super important, so focus. It's easy, really. If you see only single bonds between carbons, it's an alkane, and the name ends in -ane. Got it? If there's at least one double bond, just one is enough, it's an alkene, ending in -ene. And if you see a triple bond, it's an alkyne, ending in -ine. Now, one more thing. Alkanes with all their single bonds are called saturated. Think of them as full. They can't hold any more hydrogens. Alkenes and alkynes are unsaturated. And for the exam, remember this link to hybridization. Single bonds mean sp3, double bonds mean sp2, and triple bonds means sp. Got it? Good.
So these hydrocarbon chains are cool, but they're a bit plain, like a basic white t-shirt. What if you want to give it some personality, some style? Well, you add something called a functional group. It's exactly like adding a cool logo or a badge to that t-shirt. It completely changes its identity and what it can do.
For your exam, you really just need to focus on these 3 big ones. Slap an OH group on there and damn, you've got an alcohol. Think ethanol and hand sanitizers. Stick a CHO group on, and now it's an aldehyde. And if you add a COOH group, you get a carboxylic acid, like the acetic acid that makes vinegar sour. See? Each little group gives the whole molecule a brand new personality and new powers.
Okay, we've met the compounds, but what do they actually do? Let's quickly run through the key reactions you have to know for the exam. And then we'll see how all this fancy chemistry actually helps you get clean every single day. Yeah, I'm talking about soap.
You absolutely need to know these 3 reactions. Number 1, combustion.
That's just a fancy word for burning. You take any hydrocarbon, add oxygen, and you get CO2, water, and a whole lot of energy. Think of your LPG stove. Number 2, addition. This one is for our unsaturated friends, the alkenes and alkynes. You break their double or triple bond and add more atoms in. Simple. And number 3, substitution. This is for the saturated alkanes. They're already full, right? So you can't add anything. Instead, you swap one atom for another, like you kick out a hydrogen and put a chlorine in its place.
All right, let's talk about some real-life magic. How does a simple bar of soap get all that greasy dirt off your hands? Yep, you guessed it. It's all about carbon chemistry at work.
The secret is something called a micelle. So picture a soap molecule. It has 2 ends, a long tail that hates water. We call that hydrophobic, but it loves oil and grease. Then it has a small head that loves water. That's hydrophilic. So what happens? The oil-loving tails all rush towards the piece of dirt and stab into it, surrounding it completely. They form this little ball around the dirt, and that ball is the micelle. Now, all the water-loving heads are on the outside of the ball, so when you rinse with water, the water just grabs onto those heads and washes the whole package, the micelle with the dirt trapped inside, right down the drain. Genius! Okay, let's bring it all back home. What's the one thing you cannot forget from this chapter? Let's say it together one last time so it's locked in your memory for the exam hall. Carbon equals tetravalency plus catenation, which equals millions of compounds. That is the secret. That is the answer. Do not forget it.
And that's our rapid revision. But before you go, just think about this. We've seen that carbon can do everything from creating life itself to just cleaning up a greasy mess. If it has that much power, that much potential, just imagine what other incredible, world-changing materials we could create if we truly master its chemistry. The possibilities are endless. Okay, that's it for me. Go ace those exams. All the best!